Hi, my name is Tarun and this is my projectile motion lab. So for the introduction, the purpose of this lab was to analyze the motion of a projectile launched with an initial velocity, and the observed trajectory will be compared to two computational models, one that includes the effect of gravity and one that includes the effect of gravity and drag. The object I used was a paper ball, and the observed position was calculated using tracker software, and the predicted motion was uh, created using ClosScript. This lab will help demonstrate the principles of Newton's second law and kinematics in two dimensions, as well as the effects of drag force on projectile motion. So, basic rundown of the procedure of the lab. I first defined my variables and system. My system was a paper ball, and the surroundings was the environment, the room, and the air. I first recorded the video of the paper ball being launched. I then imported the video into the tracker software and marked the center of mass of the ball accurately. And then I developed a computational model of the motion of the paper ball using the starter code from GoScript. I then generated two graphs, one that included gravity and then one that included the effect of gravity and drag. I then analyzed and compared all three sets of data to identify similarities, differences, and sources of error. So there are three main fundamental principles. The first one was Newton's second law related to the momentum principle, and it states that a system's total change in momentum is equally proportional to the net force applied on it. The second was drag force, a force which is resistive and that opposes motion of an object through a fluid medium, and in this case, the medium is air. The third principle was gravitational force, which is a force that attracts or basically that pulls objects with masses towards each other. And in this case, it was the paper ball and the earth pulling each other. So this shows my observed motion. On the left, you can see me using the tracker software, and the red dots symbolize the center of mass frame by frame. And then on the right, you can see the position versus time graphs in the x and y direction of the observed motion. Now, for the computational model, the first one I did was the one that included only the effect of gravity. I first initialized my positions and velocities for the paper ball. I then set my drag constant equal to zero because there was no air resistance. I then set the net force on the paper ball equal to only the effect of gravity and nothing else. I then uh, typed out the velocity and position update formulas to calculate the right velocity and positions for the graphs. So the second graph included the effect of gravity and drag on the paper ball. So that's why, in addition to the code previously written, I had the drag coefficient be 0.005 instead of 0 now because there is air resistance. And then in the net force calculations, I also included the force of drag to be acted upon the ball. So to compare all three graphs, it is quite clear that the predicted model, including gravity and drag, is quite similar to the observed motion because in the real world, air resistance is a very real force acting upon the ball, while the model with only gravity is slightly below what is supposed to happen because it does not consider air resistance at all. So the possible sources of error. One of the source of error is that the paper ball used was not completely spherical in shape, so it had different areas of drag force on it. And the next was that due to air conditioning being present, it could have been slightly impacted the trajectory of the ball. The third is that the center of mass might not have been accurately selected due to the angle of the video while using the tracker software, and this could have led to minor inconsistencies in velocity and position mapping. So, further questions. The first question asks which model predicts terminal velocity? And I said the model that only considers gravity predicts a smooth parabolic path with constant horizontal velocity and uniformly accelerated vertical velocity. And in contrast, the model that includes air resistance too shows a curved trajectory that deviates from the ideal parabola, with horizontal speed gradually decreasing and vertical velocity approaching a limiting value due to the drag force. What would happen to terminal velocity if the object was thrown initially upward? It would still have the same magnitude of terminal velocity, but in the opposite direction. When the ball is thrown straight upward, air resistance acts downward along with gravity, causing it to lose speed faster than it would in a vacuum. And once it starts falling back down, the drag reverses direction and opposes the downward motion until the forces of drag and gravity balance again, resulting in the same terminal velocity as before, but just directed downward. That is the end of the lab report, and thank you for listening.